Hello, Dan here from howtomechatronics.com, and in this video I will show you how I converted my DIY 3D printed SCARA robot that I built in one of my previous videos to work as a laser engraver. The SCARA robot has 4 degrees of freedom, which are driven by 4 NEMA 17 stepper motors and controlled using an Arduino board. In the original video, I used an Arduino Uno board in combination with a CNC shield, but now we will use an Arduino Mega board in combination with a RAMS board. We need this combination because we will use the Marlin 3D printer firmware for controlling the robot. As for the mechanical part, I just had to change the gripper mechanism with a laser module. In this case, I am using 5.5 watts laser module, which is good enough for engraving. A cool feature that we get with this SCARA robot setup is that we can have a bigger range of the Z-axis movement, and so we can laser engrave taller objects. Also, the working area is pretty impressive considering the small footprint of the robot. It can use the area in front of it as well as on both sides. We can actually set it up to use almost the entire 360 degrees around the robot as a working area. We can do that thanks to the open source Marlin 3D printer firmware, which has options for laser engraving and SCARA robot setup. For generating the G-codes, I am using yet another open source software, Inkscape, and a plugin for it called Inkscape Laser Tools. We can generate G-codes with contours only and with contours and infill from the same vector image, and we have various options like adjusting the laser beam, travel speed, infill speed, parameter speed, laser on and off commands, including PWM control of the laser, and so on. Nevertheless, now I will walk you through the entire process of setting up a SCARA robot to work as a laser engraver. We will take a look at the design of the SCARA robot, how to install and configure the Marlin firmware according to our machine, and how to prepare the drawings and G-codes for engraving. So, let's get started. Here's a quick look at the 3D model of the SCARA robot, so you can see how it works in case you haven't watched the original video where I explain in details how I build it. The robot is designed in a way that most of the parts can be easily 3D printed. The joints are driven by NEMA 17 stepper motors, which speed is reduced with the help of some GT2 belts and some suitable 3D printed GT2 pulleys. The robot has 4 degrees of freedom, but in this case we only need 3 degrees of freedom, 2 rotations for reaching any point in the work area, and 1 linear motion for adjusting the height of the laser. The 4th joint, which rotates the end effector, won't be used, although the laser module will be attached on it. I made the holder for the laser in a way that the laser beam will be in the center of rotation of that 4th axis, so even if that axis rotates, it won't affect the final position. I designed this SCARA robot using 3D Experience SolidWorks for Makers, which is also the sponsor of this video. Yes, you heard it right. With 3D Experience SolidWorks for Makers, SolidWorks is finally bringing their industry-leading design tools to makers of all kinds at an insanely low price. Makers can now access the best SolidWorks design tools for only $99 a year. But for my viewers, SolidWorks is providing a limited time offer that will get you these tools for even cheaper. That's right, for viewers of this video, you can get this bundle today, which includes a cloud-connected version of SolidWorks, as well as browser-based design tools like 3D Creator and 3D Sculptor, at a special 20% off price while supplies last. All you have to do is click my link in the video description and create your free 3D Experience ID, which will allow you to access this special 20% off offer so you can start making with the best today. Big thanks to SolidWorks for sponsoring and supporting educational content like this. Alright, so first I removed the gripper mechanism from the robot, which was held in place with 4 bolts. The wires used for controlling the gripper servo will be now used for controlling the laser module. The particular laser module that I have works at 12 volts and can be controlled using PWM signal with just 2 wires, ground and VCC. For connecting the laser, I used the connector that comes with the module, the one with the 3 pins. The left black wire is ground and the middle, the white wire in this case, is the VCC. I soldered two male jumper wire connectors to these wires so I can easily connect them to the wires for the end effector. Then I simply put the connector in place, pass the wires through one of the openings of the holder and secure the laser module with two M3 bolts. Using 4 M4 bolts, I secure the laser module to the robot. Next, as I mentioned earlier, instead of the Arduino Uno board that I used for controlling the robot in the original video, now we need an Arduino Mega board in combination with a RAMS board. Here, first we need to select the step resolution of the drivers. Of course, for smoother motion, we should select the highest possible resolution by adding 3 jumpers for each stepper driver. I'm using the A4988 stepper driver, which has 16 step resolution, but we can also use the DRV8822 stepper driver, which has 132 step resolution. Then we can connect all the wires in place. I had all my wires marked so I don't mess them up. Here's the circuit diagram of how everything needs to be connected. The stepper motors go right above the drivers, and the limit switches, which are normally closed with 2 wires, go at the end stops S and minus pins for each axis respectively. For controlling the laser module, we will use the pin D9, which in a 3D printer setup is used for controlling a fan. This pin is PWM capable, so we can control the intensity of the laser with it. For powering everything, we need 12 volts power supply with minimum current rate of 3 amps. Once I connected everything as explained, I squeezed a little bit the wires and covered the electronics so that everything looks nice and clean. There was one more thing that I needed to change on my SCARA robot so that it works properly, and that's to change when the second arm limit switch is triggered. As the SCARA robot will be set to work as right-handed, the homing of the second arm needs to be at 0 degrees, or in line with the first arm, while being able to rotate to the left. For that purpose, I simply glued a small piece to the arm joint so that it triggers the limit switch at the described position. Actually, there is one more small detail that I needed to change. The original limit switch trigger was interfering with one of the nuts at the bottom of the arm, so the arm couldn't reach its full motion. I simply removed that nut, replaced it with threaded insert, so that when securing back the part in place, it won't stick out. And that's it. The SCARA robot is now ready to work as laser engraver, but of course first we need to install the firmware to the Arduino board. As I said, I will use the Marlin firmware, which is one of the most widely used open source firmwares for 3D printers, which also has options for laser engraving and SCARA robot setups. We can download the Marlin firmware either from its official website or from github.com. To install the Marlin firmware to the Arduino Mega board, we will use Platform IO ID instead of the Arduino ID. As the Marlin firmware is big and complex, the Arduino ID might sometimes give errors and not be able to compile it. Platform IO is built on top of the Visual Studio Code editor, and it can be installed as extension to it. This means first we need to install Visual Studio Code, then search for the Platform IO in the extension manager and install it from there. Once the installation is done, we can click the Open Project button, navigate to the Marlin folder that we downloaded and unzipped, and click Open Marlin. This will load all Marlin files in the editor, and so we can open and edit them. The two main files where we do all the adjustments according to our machine setup are the configuration.h and configuration_adv.h files. Actually, before we open the Marlin folder, we should first go to the configuration repository on GitHub, from where we can download some pre-tested configuration files which are suitable for us. In the examples folder, we should go to the SCARA folder and copy these two configuration files and paste them into our Marlin firmware. So once we reopen the Marlin folder with the SCARA configuration files, we can open the configuration.h file and edit some parameters according to our machine. The first thing here is to select the type of SCARA robot that we have. The Morgan SCARA is for parallel SCARA robots, and the MP SCARA is for serial SCARA robots, just like the one we have here. This is based on an open source design by Taylor Williams, which implements inverse kinematics on the G-codes generated for normal Cartesian systems. In my previous video, I already explained what is inverse kinematics and how it works with this Skara robot, so for more details you can check that video out. Briefly, with inverse kinematics, we calculate at what angles the two arms should position in order to reach a given x and y coordinate. The math behind the inverse kinematics is based on trigonometry, and the results depend solely on the lengths of the two arms. That being said, here we need to enter the length of the robot arms, and in this case that's 228 mm for the first arm and 136.5 mm for the second arm. The next parameter that we need to set is the zero position of the workbed. This value is entered with the Skara offset x and y values, and it's the distance from the tower or the first joint relative to the bed zero position. There's one more set of parameters that we need to adjust according to our machine, and that's the manual home position for both x and y. These values are the x and y distances from the robot arm end effector or the laser when it's in home position relative to the bed zero position that we previously set. In order to get these values, I made a simple sketch in SolidWorks with two lines representing the two arms of the Skara robot. From here, we can set the desired bed zero position and get the values for the manual home position variables. Next, we need to define the end stop connectors. In our case, we have one end stop for each axis, which is at minimum position. In addition to that, we need to define the home direction to -1, which indicates the direction of the end stops when homing. Here we should also check whether all these minimum end stop inverting variables are set to false. Then we need to adjust the default axis steps per unit value to match with our machine. These values indicate how many steps the program should send to the stepper drivers in order the motor to move 1 unit. Or in this case, that's rotation of the joint of 1 degree. Here's how I calculated these values for this Skara robot. The NEMA 17 stepper motors take 200 steps for full rotation, but as we are using 16 step resolution, that means that we need to send 3200 steps to the drivers in order the motor to make full 360 degrees rotation. In addition to that, for the first joint we have 20:1 reduction ratio, which means that we need 64,000 steps for full rotation. If we divide this value with 360, we will get the number 177.77, which is actually the number of steps that the program needs to send to the driver in order to rotate the joint 1 unit or 1 degree. The second arm has 16:1 speed reduction, so the value will be 142.2. For the z-axis we have a lead screw with 8 mm pitch, which means one full rotation of the motor will result in 1 mm linear motion. 1 unit here is 1 mm, so we need to divide the 3200 steps by 8, and so we get the value of 400, which is the number of steps needed for the z-axis to move 1 unit or 1 mm. The fourth value here is for the extruder stepper, but as we don't have any extruder here, we don't have to change it. The stepper motor direction depends on the way we have connected the wires. In case we have it wrong, we can either reverse the wires or change it here in software by setting the invert direction variables to true. We should do few more changes in order to get this Marlin firmware working. As Marlin is primarily firmware for classical Cartesian style printers, the Skara mode that it features has some small bugs which weren't solved yet at the time I was making this project. So here are all of the changes that I did in order to get it working. In the Skara.cpp, line 75, I replaced Morgan Skara with MP Skara. In Motion.cpp, I had to comment the line 1716 and 1717. In Configuration.h, comment validate homing steps, and in Configuration_adv.h, uncomment quick home. Actually, even with these changes, the homing was not working 100% properly, but I will explain the workaround I used to get it working. Nevertheless, now we can click the upload button located at the bottom left of the editor, and the Marlin firmware will be installed to the Arduino board. You can find and download this particular Marlin firmware with all the changes that I made to work with this Cara robot on the website article. Or, of course, you can download the original Marlin firmware from github.com and make all changes on your own as I explained. Alright, so once we have the Marlin firmware installed, now we need a computer program for controlling the robot and sending G-codes to it. There are many options, but I chose to use Repetier Host, which is a popular 3D printing software. We can download and use this software for free. Once we install it, we can go to Configuration, Printer Settings and adjust several things here. We should select the COM port to which our Arduino is connected and select the baud rate which is set in the Marlin firmware. In the Printer Shape tab, we should set the X and Y max values and the printer area. Once we apply these settings, we can click the Connect button and the software should connect to our Cara robot. Then we can go in the Manual Control tab and from here try to move the printer. Note that when pressing the X or Y arrows, the robot might behave weird as it implements inverse kinematics right away. Nevertheless, in order to get the robot working, we should first home it. Before we click the home button, we should manually bring the joints closer to the limit switches. When we click the home button, the robot should start moving towards the limit switches. Actually, the second arm will start moving towards its limit switch, while the first arm should move opposite. Once the second arm or the Y-axis will hit its limit switch, the first arm or the X-axis will then start moving towards its limit switch as well. Once the X limit switch is reached, the robot will go for the Z-axis limit switch. So after the homing is done, we should be able to start engraving or manually move the robot around its working area. However, if we try to do anything right away, for some reason the robot will misbehave and it will do strange movements. To avoid this strange behavior, after the homing is done, we need to disconnect the robot from the software and then reconnect it again. Now the robot will work properly. This is probably a bug in the Marlin firmware and it's there because the Cara mode in this firmware is not backed well as there isn't much interest in it. Nevertheless, if we send the G-code command G00, X0, Y0, the robot should go to its 0 position, the one that we set in the Marlin configuration.h file. Then we can activate the laser by sending the command 106 S10. The value behind S can be from 0 to 255 and it's actually the PWM control of the laser power from 0 to 100%. We are using a value of S10 here so that it won't burn anything, but it will be visible so we can see the 0 position and also adjust the focus of the laser. The focus can be manually adjusted by rotating the laser lens at the bottom and it depends on the distance between it and the working piece. It's recommended to set a distance of around 5 cm and adjust the focus till you get the smallest dot possible. In order to calibrate the machine, it's a good idea to start with engraving a small square shape so we can see whether it works properly. In my first try, the square shape was not in the right position and orientation, and that's because I have set wrong value for the manual X home position variable. Once I corrected, the square shape came out close to what it should be. So I load up a G-code of my logo and set the robot to engrave it. To be honest, looking at this Cara robot working as a laser engraver is so cool, but please note that we must use laser safety goggles that will protect our eyes from the ultraviolet light of the laser, as it's very dangerous. Also, we should use a safety respirator mask and work in open space or well-ventilated room, as the fumes produced while laser engraving are also dangerous for our health. Nevertheless, the logo engraving came out well, but I noticed that it wasn't totally square. So I got back to engraving the simple square shapes in order to find out what was causing the problem. I realized that the problem is with the dimensions for the length of the arms. As the robot is not that rigid, when the arms are extended, the weight of the arms themselves make the robot lean a little bit forward. This causes the actual dimension or position of the arms to be a little bit off. After making dozens of tests, I ended up adjusting the values for the lengths from 228 to 228.15 mm for the first arm, and from 136.5 to 136.2 mm for the second arm. This gave me the most accurate results, and now the square shape was right, though depending on the location of printing, whether the arms are fully extended or not, the accuracy could still vary. Alright, so lastly, let me show you how I prepared the drawings and generated G-codes for laser engraving them. I used Inkscape for that purpose, which is an open source vector graphics software. Here, first we need to set the page size to the size of our working area. As an example, I will show you how I prepared the Arduino logo for laser engraving. I downloaded an image of the Arduino logo and imported it into Inkscape. Using the trace bitmap function, first we need to convert this image into a vector format. We can only generate G-codes from vector shapes, and for that purpose I used a plugin called Inkscape Laser Tools. We can download this plugin from GitHub and we can install it by copying the files from the zip file and pasting them into the Inkscape extension directory. So once we have the plugin installed, we can go to Extensions, Laser Tools, and open it and use it for generating a G-code. There are several options to set and adjust with this plugin. As we connected our laser to the D9 pin, which is used for controlling a fan, we can activate the laser by sending the command M106. Here we can choose whether the G-code will only contain the contours of the shape or the infill as well. We can set the laser travel speed, the laser infill speed, and the perimeter speed. When choosing an infill, for example if we want to lower the intensity of the laser in the infill area, we can add PWM value to the M106 command to set the laser intensity. For example, M106 S128 for 50% laser power. We could achieve similar effect to this if we leave the laser power to 100% but increase the travel speed in the infill area. So these are actually settings that we should play with to see what works best for us. In the Preferences tab we can select to remove tiny infill paths, and in the Bounding Box tab we can select Generate G-code for Bounding Box Preview. This feature is useful as it generates preview code of the area where the drawing will take place, and so we can position our workpiece precisely. So once we generate the G-code, we can load it in the Repetier host program. As this is not 3D printing but just travel moves, we should select the checkbox Show Travel Moves to preview our G-code. We can finally click the print button and our Scar robot will laser engrave the workpiece. I already said, watching this Scar robot laser engraving is so satisfying. We can laser engrave so many things with it. A good feature is that it has adjustable Z-axis, which means that we can laser engrave taller objects, like for example this wooden box for my Forstner bits. I engraved my logo on the front and a text Forstner bits on the back of the box. Here's an example of engraving the same vector shape, a Batman silhouette in this case, with just contours and with infill on closed loops. Of course, when engraving with infill, the time needed to finish the job is much longer, but also the final appearance is much better. Nevertheless, at the end let me show you how I engraved this huge drawing with area of 600 by 450 mm with this Scar robot. I placed the robot on top of the workpiece so that it can reach the front and the two sides. Then I manually adjusted the workpiece and the robot to be in the middle and parallel to each other. In the Marlin firmware, I set the 0 position to be at the bottom left corner of the workpiece, which is 300 mm away from the robot in X direction and 150 mm in Y direction. We should mind the signs when defining these values. According to this, I also changed the manual X and Y home position variables. After uploading the firmware with the new values, I homed the robot as explained earlier and sent the laser to the 0 position. Then I activated the laser so I can further adjust the workpiece orientation if needed. By sending G01 commands, which do straight lines, I could check and adjust the workpiece to be positioned properly. Now, as for preparing the G-code for this engraving, I made a template with this configuration of the workpiece and the robot in Inkscape. From here I can see where the robot can reach with the laser and, according to it, modify the drawing. For the drawing I downloaded an image and converted to vector image by using the trace bitmap tool as shown earlier. Then I rescaled and positioned the image as I wanted, and using the erase tool I deleted the areas where the robot is and the area which is outside the robot reach. Then I generated the G-code and let the robot do its job. It took 4 hours to laser engrave this drawing. Once it finished, I wanted to fill the empty area where the robot was. For that purpose, I repositioned the robot and the workpiece, as well as changed the Marlin parameters so that the new work area of the robot is the empty space of the workpiece. Overall, this method requires some work for setting it up, but still it works great. I really like how this engraving turned out. To wrap up this video, although there were some problems with the firmware, I managed to find workarounds to them and get this car robot working as a laser engraver. If we take a closer look to the engraving, we can see that it's far from perfect. The robot is not that rigid and has some backlash, and therefore we cannot get precise and smooth movements. However, the things we learned in this video can be implemented in any SCARA robot, so you can definitely get better results. I hope you enjoyed this video and learned something new. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.